So this is, it's been a pretty interesting kind of spectrum of talks today. We're starting out with some very social scientists, and now we're moving a bit more towards the kind of computer science AI direction. So this is going to be kind of probably the furthest along the AI spectrum, where I actually have a new technique for interpreting these LSTMs that I'm going to talk to you about. And so this is some work on basically moving beyond just looking at word importance when we're interpreting these neural models, because they're actually learning a lot more than just what words are important. And so this is some stuff that started this summer when I was at Google Brain with Peter Liu, and is also joint with my advisor here at Berkeley, Bin Yu. And it's under review at ICLR, which is the big deep learning conference. And so, as most of you have probably heard, if you have a supervised learning problem and you have enough data, then deep learning models are pretty great, and they're going to give you some pretty good predictive accuracy. However, the trade-off that's come with the use of these models is that although they're really accurate, they're generally largely black boxes, where you have some data, you put it through some mysterious mechanism with a bunch of equations that you don't really understand, and then at the end of the day you get a prediction which most of the time is going to be right, but you don't really know why. This is nice because prediction's great, but as we've seen today, we often care about a lot more than just the prediction, right? We want to know where this prediction came from and what relationships and what insights we can actually draw from our data that these big, complicated neural models have learned. And so the way that we kind of formalize this into a problem that we can attack is through something that we're calling algorithmic interpretability. And so the basic idea here is that we look at a particular prediction made by one of these models, and we aim to come up with some form of explanation that describes the internal workings of this model and can help us to understand why it actually made this prediction. It's worth noting that we view this as kind of a subset of general interpretability, where we're looking at how to extract this information, but leaving open the question of what to do with this information once you actually have it out. So this is something that I imagine some people here may be interested in. It's actually, I have some ongoing work in that space as well. And so from now on, I'm going to be focusing on a particular kind of deep learning model known as long short-term memory networks, or LSTMs. And if you don't know what that is, or if you can't remember the 6 updated equations, basically all you need to know is that this is kind of the dominant deep learning model in text. And Chris Manning, who's a pretty famous NLP researcher from Stanford, gave a talk at Simon's about 6 months ago, where he had a slide that a lot of people talked about, basically saying that if you want to get to state of the art in an NLP problem in 2017, all you have to do is throw a particular kind of LSTM at a problem. And so, the big question that I kind of purposely left open in the last slide is how do we actually explain these predictions, right? In particular, what kind of vocabulary or terminology should we use? And so moving forward, we're going to be looking at the problem of binary sentiment analysis, which a lot of people have already talked about. And so, kind of the simple, stupid thing that people have done a bit in the past, over the past year or two, has been, if you have this kind of toy review here saying the movie was good, well, everyone's going to tell you that's a positive review. And then if you want to explain why it was positive, then you can just kind of pretend that this big complicated LSTM is more of a bag of words style classifier, and try to isolate what the important words are, right? And so in this case, it would say that, okay, our LSTM has learned that good is a positive word, and because most other words are pretty neutral, then it's produced a positive prediction. And for examples as simple as this, that kind of sort of makes sense, and people can write their prefixtures and get their papers. But if you add even one word into that review, all of a sudden things get a lot more complicated, where you can no longer really point at a single word in this review, the movie was not good, and say, aha, this is why it's negative, right? Of course, what's actually happening here is that we have this negation relation where, having the single word not doesn't really tell you it's negative, having the single word good certainly doesn't tell you it's negative, but it's those two it's those two combined and that interaction between them, which is what leads us to classify this review as being negative. And so, what I would argue is the better way of explaining this prediction is being able to say, hey, the word good here on its own is pretty positive, and not is a little bit negative, but again, it's this interaction between the two of them. And so basically what we've done here is we've added an extra degree of freedom, which allows us to describe not just word level importance, but also this kind of compositionality, which is exactly the difference between what LSTMs capture and what bag of words models capture, right? And so, yeah, it's really these kinds of examples that are where neural models can kind of beat the existing bag of words stuff. And so, the lesson that I'm kind of beating to death a little bit here is when you have a really nonlinear model like an LSTM, you need a nonlinear explanation, right? You can't just focus on these important words. And so our solution, in more general terms, is to say not just, hey, these are the important words, but to actually specify importance scores for any arbitrary phrase within the input. And so these scores are also not additive, which is to say that the score for not good is not equal to the score for not plus the score for good. And so this also allows us to infer interactions between variables, right? And so this is what I was talking about before, where we had the interaction between not and good making this review be negative, and we'll actually see later on that these interactions capture negation in a more general sense. And to give you a bit more of this is my kind of very high level simplification of the math that went into the paper. If you want some of the more some of the details, then you can come talk to me later or look up our paper online. But basically how we do this is, if you look at a high level, how LSTMs work is they take in a sentence and then they output some logistic regression coefficients, which are fed through logistic regression in order to get your final output. And so what we do is we come up with a decomposition of those features which are fed into the LSTM into a sum of two terms, where one of those terms corresponds to contributions made solely from the phrase which we specified, and the other contributions correspond to basically everything else. Okay, and so now that I've kind of given you a sense for what we're trying to do here, let's talk about the evaluation and hopefully convince you that this is actually something that has some worth to it. And so for the setup, what we did is we took two pretty standard benchmarks in the NLP community for binary sentiment analysis. First, we had the Stanford Sentiment tree bank, which consists of about 10,000 reviews from Rotten Tomatoes. And they had Mechanical Turk workers provide human labels for both all of the phrases within the parse tree as well as the review as a whole. And then we also looked at the Yelp polarity data set, which consists of about 600,000 reviews from Yelp, where the labels come from whether or not the star rating is above or below 3 stars. And so we trained pretty accurate LSTMs to do our interpretations on using pretty standard techniques in this space. And so then we decided to look at some of these instances of compositionality that you would expect to see in sentiment analysis. And so first what we did is we looked at the Yelp review data set, and we decided to look at instances where you have relatively short phrases of at most 5 words with contrasting sentiment contained within them, right? And so if you look at this first example on the left, you have the phrase "used to be my favorite," right? And this is in reference to some restaurant where they're saying it used to be my favorite restaurant. And so what's happening here, right, is you have the word favorite, which is actually a very positive word in the context of sentiment, but it becomes negative when it's contained within the broader phrase "used to be my favorite." And so we have a few different baselines up top. The middle one is actually some prior work from myself that I did with Facebook. But basically the important thing to take away is that the top 4 the top 4 methods all identify favorite as being anywhere between neutral and very negative, whereas my method is able to identify that favorite is very positive, right? And this is actually pretty troubling because it's showing that in these instances where you have this compositionality that LSTMs are actually learning, a lot of existing methods are providing you the exact opposite of the truth, right? And that there's this kind of like unspecified contextual information that's being baked into these word level importance scores that we're able to fix when we actually explicitly account for this compositional structure, right? And when we have something similar happening with this phrase, not worth the time. Of course, this is anecdotal, and anecdotes aren't worth all that much. And so we actually did a search over the entire data set where we searched for similar situations and tried to make data set level claims rather than just anecdotal claims. So in particular, what we did is, because the alpha is so big, you can actually train a pretty decent n-gram logistic regression model. And so we can use that to get phrase level sentiment labels. And then we can use that to conduct a general search for these kinds of situations where you have a very negative or positive phrase contained within a larger phrase of opposite polarity. And then what we do is we can plot the distribution of scores from positive phrases or from positive subphrases and from negative subphrases. So in the previous example where we had used to be my favorite, here we would include the word favorite under the positive distribution. And what you should take away from this is basically that the anecdotal evidence I was showing in the previous slide holds up, where for all the previous 4 methods, which is everything except for contextual decomposition, which is our method, the distribution of importance scores are basically the exact same for both negative and positive words, which is to say that, again, if you have any kind of compositionality, any kind of interesting stuff happening, then like previous work couldn't really capture it. Whereas, we have a pretty clear, if not completely distinct, difference in this last contextual decomposition plot. Okay, and so this is kind of troubling, but it's a little bit more into the weeds. But if we look at the Stanford Sentiment data set, we can show things that are even a little bit more troubling, where now we're looking at instances not just of relatively small subphrases in the scope of the review, but cases where a very sizable chunk of the entire review is actually of opposite polarity to the review level label. Right, and so you can look at examples like this one where the review says, it's easy to love Robin Tooney, she's pretty and she can act, which is quite positive, but it gets harder and harder to understand her choices. And so, again, the first part of this review is quite positive, but there's this similar narrative where, where prior work basically has the document level information leaking into these reviews, where because the global review is negative, it's, even though this first half is pretty clearly positive, it's labeling as negative anyways. And in some sense, this is even more troubling because you don't, like, here half of the review is positive and it can't even capture that, just because this compositional structure is getting baked in. And so as before, we did a population level analysis. And here it's not, you don't have the distributions on top of each other like you did before, but they're still generally not that great. So if you look at cell decomposition in the middle of the top row, the distributions are actually the opposite of what you'd expect them to be, where most of the negative phrases contained within positive reviews actually have positive scores, and vice versa. And for integrated gradients, which most people would probably view as kind of the strongest baseline in this problem, it may not be easy to see from your perspective, but about 90% of the positive phrases actually have importance scores less than 0, which correspond to a negative rating. In contrast, for contextual decomposition at the bottom, again, there's a pretty clear, pretty reasonable gap between these two distributions, which again indicates that if you account for this compositional structure, you can do a lot better. And finally, and this is in some sense the most interesting aspect of this work, and I alluded to it before, is that because these phrase level scores that we're getting out are non-additive, we can actually start to look at these interactions between variables. Right? And so what we did here is again, we conducted a search across the Stanford Sentiment data set using the human-provided phrase labels in order to search for instances of both positive and negative negation. Right? Where by negative negation, I mean this movie was not good, and by positive negation, I mean this movie was not bad. And so, what we can see here is basically that those interactions I was talking about before, where you take the score for not good and subtract the scores for not and good, actually basically capture quite well what you would expect them to do, or what you would expect an interaction score to look like, right? Where you can see on the right here, most of the positive scores, which are the blue-purple ones, are quite positive. Most of the negative scores are quite negative. For reference, we also provide the distribution of just all interactions. And you can see that the negations are very much on the tail ends of this distribution, which would empirically confirm the fact that that most people know that negation is one of the most important interactions that goes on in sentiment analysis. And this is something that just qualitatively hasn't really been seen before. There's one method that came out of Stanford earlier this year that they didn't try to do it, but you could try, and this is kind of what happens, where it captures it about half of the time. And yeah, so this is, to my knowledge, this is actually the first instance of people being able to capture, actually being able to show at any level that LSTMs are able to capture these kinds of, that they're able to capture a negation relation, which we think is pretty exciting. And so to conclude, I've introduced this new approach for interpreting LSTMs, which we call contextual decomposition, which we can use for extracting important scores for not just words, but also phrases and interactions. We showed that we can have these qualitative improvements of our importance scores when dealing with compositionality, which, as I discussed, are really the most interesting cases to look at when you're looking at the differences between LSTMs and bag of words. And finally, we showed for the first time that LSTMs can actually capture negation. So that's it.